Well, happy almost Friday, folks. Looks like it's official. We can get started. Today's week, we're finishing off chapter 15, and then we're going to move into chapter 17. We're probably not going to spend a lot of time in here, but we'll finish off the week on this chapter here. That's not on a lot of announcements, but maybe just to add a little bit more, I would say chapters 13, 14, 15 are pretty intense in this class, especially if this is your first statistical class. But once we get to here, we're essentially over the hump. The purpose of chapters 14 and 15 is just to lay down the foundation of what does statistical inference look like, what is hypothesis testing, what is confidence intervals, what does essential limit theorem say, and it's a lot of information out of nowhere. But chapter 17, with all that framework laid down, the course starts to cool off a little bit. We're just going to be doing method after method. And this is also informed by grade data. Usually people's scores improve right around here once we're getting into these chapters. It's kind of curious. In a lot of other classes, it's kind of the opposite case. The difficulty just steadily progresses. But this is a slightly different and weird class for those kind of reasons. We'll finish off a pretty intense topic in chapter 15, computing the power of the test. And then we'll lean on everything we've been doing all along to get through these subsequent chapters. Well, any questions at the moment, folks? Okay, well, let's get started. We left off chapter 15, breaking a problem kind of in half. Always kind of unfortunate when that happens, but let's kind of refresh what we're looking at and then move through the rest of the problem. We're looking to the context of emission of SO2, so acid rain in the Canadian rainforest. We're informed black coffee has acidity, well, a pH rather, which is acidic, near 5. And we gave other information about the problem that in different days in the Canadian rainforest, the pH measurements follow a normal distribution. And that normal distribution has a standard deviation of exactly 0.5. That's kind of interesting data, but if we run with those assumptions and consider them plausibly accurate, here's what we did next. We framed a hypothesis test where the null hypothesis is that the pH is at 5. The alternative hypothesis is that the pH is way worse, less than 5, so highly acidic. Well, more acidic, rather. We tested it at a 5% significance level. We are going to test it, rather, once the data is collected. This whole study is really more about the planning phase. We didn't even say what the sample size is going to be, but we'll say what it should be after we're informed on what the power of the test is going to be. First thing we decide on is the significance level tuned well? Well, we do that by taking a look at a type 1 error versus a type 2 error. And a quick rundown on that is type 1 error is a probability of rejecting the null hypothesis when it was actually true, whereas a type 2 error is failing the null hypothesis when we really should have. An alternative, a specific one, is actually true. So we very painstakingly wrote out what these statements would be in this context. These statements, being a practical interpretation, can't have too much symbolism. Really, no symbolism at all is in here, except maybe notation for pH. And we have to use the context. We have to be talking about the acid rain, the pH values, things happening in the Canadian forest. That kind of stuff has to happen. I don't think I ever said Canadian forest, but we did say forest. We did talk about rainfall and pH. So all that is bringing in the context. Well, type 2 error is where we're going to get power, because power equals 1 minus beta. And actually, power is the thing that we want. So once we compute power, if we want to say what beta is, we just do say beta is going to be equal to, change this all around, 1 minus power through the complement rule. But because calculating power involves beta itself, we should write down what a type 2 error is, and that's what we did right here. In a type 2 error, we say the study failed to find significant statistical evidence that the population mean rainfall is less than a pH of 5. That's the alternative, less than 5. But these are conditional probabilities in the sense that we always say given that something else happens, and the something else is that the population mean is actually exactly 4.7. That's the specific alternative we mentioned in this two-way table for type 1, type 2 errors. And it was informed to us by this information. The meteorological or ecological experts have somehow informed the people leading the statistical research here that differences smaller than 0.3, they're just too small. So because of that, we go to our null hypothesis, or rather our alternative, and say, well, if it's close to 4.9, close to, that's basically 5 to us. We're not too worried about that. We're worried when it hits a pH of 4.7 or lower. And so that's where probability of type 2 error comes into play. It was informed by the effect size, taking a value of 0.3, subtracting it from the null hypothesis to inform us. That's your specific alternative right there, 4.7. So lots of hoops to jump through, but does that logic make sense, folks, on why 4.7 here? Okay, and we briefly explored this question right here. In your opinion, which type of error is more concerning to industry in Canada? And both errors are bad. I mean, whether we make a type 1 or type 2 error, it's going to eventually hurt everybody, the fact that we made a mistake. This question is about what is the more immediate people who are going to get hurt right away. And seems like the class overwhelmingly said, looks like it's a type 1 error, is that situation. Or excuse me, let me roll that back. Yeah, type 1 error. What would happen in a type 1 error? Let's imagine it. In a type 1 error, we've rejected the null hypothesis. We've accepted that this is the truth about the population, that there really is rampant acid rain going on. This could now affect all sorts of interesting things in Canada in their legal system. Lawmakers can make changes influencing industry, stymieing their growth, or even worse, potentially. So it looks like type 1 error is the big danger on this one. Let's see if we can express that. We'll say here, if a type 1 error occurs, then we conclude, sure, we conclude mu less than 5, but let's say what the larger thing we're concluding industry may be responsible. Well, I shouldn't say it that way. We should say acid rain is a big problem in the Canadian rainforest, and people are going to look at industry next as a way to control it potentially. So that's a huge concern to them. So we'll say here, then we conclude acid rain is a major problem in the Canadian forest. Which may prompt lawmakers to legislate legal action against industry in Canada. That is a longer statement than I intended, but there it is, barely fit. And that's one way to give a response here. I think some people in the class might say, from their point of view, type 2 error is the worst one in industry. And if that's your case, if that's you, I think that's terrific. This is really an opinion type problem, which is weird in a math class, right? Even in a statistics class. But as long as you explain your choice and you're saying logically sound things relative to the context and what's going on with the hypotheses, either response would have been fine, type 1, type 2 error. I'm sure that there's a good argument somewhere for type 2 error being worse for industry. It just wasn't the first thing that I personally saw in this problem. But any last questions or comments folks who want to add to this here? Other than I have part B twice, I'll look into that next. Okay, and because this is going to bug me, let me just do a little bit of work here. This is part C. D, I think this happened to me last semester. I need to get control of those parts at some point. This is F, G, and H. Geez, this is a long problem, but there's a lot to say about power. So let's keep on going. So we've explored what type 1 error is, what type 2 error is. We've made a determination on which one we think might have been worse. And by the way, now that we said it was a type 1 error, it's interesting to answer this question. What would you all say the probability of type 1 error actually would be in this problem? Let me see if I can scroll out to a good spot. Okay. Anyone see what the probability of type 1 error turns into in this problem? It's really tricky in a way. And it's tricky because it's one of those problems where it's no computation. So when you put it down a number, it almost feels like you did something wrong because we really didn't actually have to do anything. There's one number somewhere here. Usually it's closer to where the statement of the hypotheses are. That's directly telling you probability type 1 error. Anyone spot where it is towards this part of the document? It is, exactly. So this right here, that's the cutoff of when we would reject the null hypothesis. We compare this against the p-value, but it is also directly the probability of a type 1 error. Very, very unusual in a certain sense. You could look up on the notes for a fast explanation of why this is the case. But this alpha equals 0.05 is probability of type 1 error. And if we felt like type 1 error was the worst problem or the worst outcome for making an error, we could have controlled that by making alpha smaller, maybe a 0.025 or a 0.01, for example. And that would have worked out for controlling what we believe might have been the worst error. However, it inflates the probability of a type 2 error. And this one might be worse for ordinary Canadians. So if we take them into consideration, dropping this to a 0.01 may not be the best outcome if we're worried more about Canadians versus specifically industry in Canada. So there's a lot to consider, but if they landed at 5%, we come down here and just say, let's make a quick statement. Probability of type 1 error is always alpha. And in this problem, we just had to say what that value was, 0.05. Well, any questions at all, folks, on type 1 error? Okay, astoundingly fast. It's kind of fun in a way. But watch out for this on homework problems or exam problems because it's easy to get stumped here because there's really not much to say. If all you put down was 0.05, that was it. You just had to observe that significance level. Now for the next part, we want type 2 error, but rather we're going to calculate power directly and then just say what probability type 2 error is as a side comment. And this is where we're going to begin in part D. There's actually a lot of syntax involved with this. Well, maybe not a lot, but it's tricky to assemble what we have. It tells us next, suppose that differences smaller than the pH of 0.03 are not considered to have practical significance. And that's a huge statement right here. What they just said is the effect size is 0.3 by that statement. And now that tells us, well, our specific alternative is going to be from this piece of information right here. So the way we get that piece of information is we say the specific alternative hypothesis is, let's grab the hypotheses so we can visualize as we think about it. Because this is a left tail test, we go HA mu equals mu A minus effect size. So once we have the effect size, we're all set. And I made a typo there. Let me fix that. That was meant to be mu naught, not mu A. Actually, let's leave these hypotheses here just as a quick reference for what we're about to do. So the mu naught was this value, Also the value of the alternative hypothesis. Usually we're looking over here. That's the value to be tested. So we took mu naught, which is 5, subtract the effect size, which is the 0.3 we see over here, and that's how we get the specific alternative. HA mu equals 4.7. So it feels weird. An alternative hypothesis really needs to look like this: infinitely many possibilities, never equality. But if we're calculating power, you need a specific value to make that power computation actually happen. So now we're ready to begin in computing power. So here's what the objective is. Recall we didn't even select a sample size yet. This is kind of like the first problem in the notes where we were trying to find out the sample size to get the right margin of error. But in a hypothesis testing, we're trying now to find the sample size to target the right amount of power. We're going for 95% power on this test. So what sample size is required? Some people might say 1,000,000. And to some degrees, you're right, but that's not in the spirit of this problem whatsoever. Think from the point of an economic standpoint. Statistics is expensive. Grabbing random samples, analyzing the data is very expensive. What we really want is the smallest possible sample size that gets us just above or exactly 95% power. So we're trying to optimize as well. We're not trying to say, well, just 2,000 people should do it. No, we want specifically the smallest sample size possible. Unfortunately, this is how law statistics works. We know larger sample sizes are bigger, but we're constrained by just the economy of the situation. Sometimes they're just not feasible or affordable in any way. So to get that power, we could just write down the syntax, but the syntax on this is really weird. And the best way to get it down just right is to draw a picture. The picture starts by looking at our null hypothesis and then our specific alternative. So let's start right here. H naught, U is 5. Let me add it just a little bit more space. So if we take H naught, mu equals 5, then this directly implies, by the good old central limit theorem, chapter 13, that X bar is distributed. Here's the sampling distribution of the mean, in other words, as 5 goes in, coming directly from over here. Then we take the value of sigma. It's up there. Recall that one is 0.5. And divide by the square root of the sample size. Recall, we don't know what n is, but this is the expression for that. Now, once we have that down, we just draw it out. So here is the normal distribution curve relative to the null hypothesis right here. This is like the hard part. We want to draw something that's decently easy to work with, symmetric, and that ought to do the job. So the center of this normal distribution is directly at the value from the null hypothesis, 5. And let me throw in another value that I did not manage to screenshot. These hypothesis tests were relative to the significance level alpha at 0.05, and it's also a left-tailed test. Because of all that information, we go down to the axis right about here. Call it Z. There's going to be a cutoff that goes this way. I'm drawing Z to the left only because this is the picture for the left-tailed test. Shade to the left, a value that looks like it's about 5% of the area under this curve. And this is where alpha goes. Whatever its value is, plug it right up here. It's just going to be an area under that normal curve. And at this point, we can say exactly what Z is, but let's actually build the next part of the diagram and then just put it all together at once. Any questions first, folks, for this region here, or this portion? Okay, now to get the power of the test, we put in a second normal distribution. This is where it gets a little dicey. So this is not a diagram you want to just throw onto the paper. This is a diagram that you want to see built step by step so that you can really internalize all the key components. So I want to build a curve that looks just like this one, exactly, except it's shifted to the left, centered at 4.7. relative to the specific alternative. So here's my best attempt at drawing that curve exactly. About like that. Actually, let me move it over just a little bit to here, because it's a little bit easier to see what's going on with power if we get it to overlap a little bit better. Say like that. So I want my curves to overlap a little bit. The
And
amount
Mr.
they
Jacobson,
yeah, go ahead.
there's just a question in Zoom.
Oh, thanks for spotting that. That was totally invisible to me. Sorry, Summer, you said, how do you find Z star again? So this Z right here is relative to, oh, that was the wrong thing to do. It comes from, let me see if I can eliminate that. There we go. It comes from taking this curve right here, which came from the null hypothesis. Then we grab the fact that we're doing a left tail test from that alternative hypothesis right there. Then we take the alpha level, 0.05, and put that area to the left right here. Is that what your question was mainly about? Just assembling where alpha goes and where Z goes? Or is it more about how do you get Z once the diagram is built?
I'm more confused on like how to get Z in general. That's been kind of confusing throughout like the whole time we've done it.
Gotcha. Z is interesting because it has loads of different interpretations. When you say Z in general, you could be referring to a Z star, and this has a context where it comes up in X bar plus or minus a Z star times sigma over root n. Here we're doing a confidence interval. But then the other context Z can come up is Z as a test statistic where Z equals X bar minus mu naught divided by that same sigma over root n. So this is the one for hypothesis testing. And the one above is the one for confidence intervals. And this one is just slightly different. It's kind of like doing the test statistic right here, but it itself has a slightly different meaning. It's a cutoff value that produces a rejection region so that if any test statistic did end up right here, we would reject the null hypothesis immediately. But this Z, again, it takes on a different role. In this case, all we're really doing with Z is writing out Z equals Q norm. We throw in the area, alpha. Then we throw in the model right up here through the central limit theorem and go mu, whatever that value was, sigma over root n. And that's the sigma over root n coming from this part. And this is the syntax that it's going to give us this Z. Slightly related to the test statistic, but not exactly. Test statistic is really doing this formula. And as a critical number Z star, this is more, we're just doing a confidence interval. But does that help to think about that question so far?
Yeah, it does. So for these, is this something you could calculate without our studio, or is this something that we would be given on an exam?
This is something that we would have to calculate with RStudio. But if it was an exam problem, I couldn't make you do the power computation. I would have to give you the power and ask you to interpret it, something along those lines. So yeah, we're
Oh,
going to have to use QNorm through RStudio to get that actual value.
okay. I think that's where I was getting confused on like the actual computation, if it's something that we were supposed to do or if it's something through our studio.
Gotcha. I'm glad you asked that question because this is good to clarify as well at the same exact time. Other questions at the moment? Yeah.
In your equation of right, I think it gets 0.5, so just 0.5.
Oh, thanks for mentioning that. That's going to make all of the difference on this. 0.05. Thanks for spotting that value there. Other questions or comments at the moment? Okay, so we've got good amount of the diagram in here so far. Let me see if I can control, oh, probably not. Let's see if we can draw that curve one more time. The next curve we're drawing is relative to that right there, that specific alternative. And let's write that out actually. If we have HA, mu equals 4.7, then this happens again. This is just a different reality for the central limit theorem. Come over here, this will imply through the central limit theorem that X bar is distributed normally. And now this time the true mean is 4.7, and 0.05 divided by square root of n is the same from this part of the model over here. So the only adjustment is the center. And that's why the curve is going to have the same exact shape. It's not wider, it's not narrower. It's just located in a different central region, 4.7 now. So now if we draw that out, it's going to be something about like that, trying to match up the height and the width. Then let me just move it over a little bit. Trying to get some overlap just for the sake of visualizing it. And this is now relative to that curve. This distribution is relative to that curve. Okay, so we just about have everything. Next thing we could do is we take this little dot right here, which caused a vertical line segment to go up right at the blue curve, but actually it keeps on going up. It stops wherever the blue curve will stop. And this curve goes to the right forever. So I drew them so that they're overlapping a good amount to visualize it better. But if it was this situation, that curve here would still eventually hit the blue one at some point. We're just about where we want. This is the exciting part where we get to say, let me just come up with a good color for this. This part right here, that is not a good color. Let's go with this one. This part right here, under the blue curve, going all the way through to the black boundary, overlapping through the purple stuff as well. This right here is power. So if you can compute the area of that region, you have the power of this hypothesis test. And now with the diagram assembled, we're about ready to specify the syntax fully. So you first draw the one normal distribution, draw a second one as identical as you can, but move it to the left a little bit. This Z right here informs us on how to get this cutoff value, this vertical line segment. And the way we compute Z is we put just the significance level alpha itself right inside here. If it was a right tail test, we would just put lower dot tail equals false. And you could write the syntax all in one go, but let's visualize this as kind of a function composition instead. We can now write out that power equals, it's this area under the blue curve. And because this time we're getting area, we'll go P norm. We need a cutoff value to get the area, but that's exactly what Z was. The area to the left of the black line segment is power, so just throw in Z. That does the job. Now you have to recall you're working with this model, the one in blue, so you need a different value for mu. This will be mu A, the specific alternative. The next one is going to be, well, same exact as before, sigma divided by root of n. So this is our full syntax of getting power whenever we're dealing with the left tail test. We'll describe the syntax for the right tail test as well. It's essentially the same. You put right dot tail on both spots. That's kind of nice in a way, but your diagram does change a whole lot. Keep that in mind. Let's implement this and just see what we get all together. Any last questions or comments so far, folks, before we jump into RStudio? Okay, for RStudio, let's just design a script that's going to work in pretty much any situation. But if you use this again, let's also put in a guide. Left tailed test power. That way, make sure you read the first line here and not misuse the syntax if, say, you're doing a homework problem in chapter 15 and it's a right tail test. So that'd be a easy mistake to make. Next thing we do is we go define mu naught. I'll just write it mu sub zero, mu zero rather. In this problem, it's going to be this value here, coming from the actual null hypothesis or the actual alternative hypothesis. Usually you look here, well, me personally. So this one's going to be specified as a 5. Next, you need that value, this value in the specific alternative, the one that told us the center. Actually, let me put here 4.7, just to emphasize that that's the center of this distribution. So we'll call it mu A. And this problem, it's 4.7. Okay, what else would we need? We need a sample size. We're looking for, remember, the smallest sample size that gets us at or just barely above 95% power. Let's start at 10, hoping we'll save some money, and then we'll see how much extra we have to spend. So what else would we need? We need a sigma, right? So let's specify that as well. That one is at 0.05. What else would we need? There is one more thing. Just looking at this first part that's going to go in the script, we also need the significance level alpha. So let's just write that in as alpha. Geez, where's the home row? Alpha, there we go. Gets 0.05. So same value there as well. That's kind of distracting. Now, finally, putting this all together, here's the two pieces that we need to get the rest of the computation. So on the field above, that's the stuff that you would change on each new problem. And the stuff below is just going to be the computation. Let me extend this just a bit. So following the same syntax on paper, let's go z gets q norm. It's q norm because we don't know the z value, but we know the area value. It's kind of an inverse problem. The area, again, is just alpha. No harm in putting 0.05 right here if you prefer. But if you want a script where you can just control, toggle these values here, this will always work no matter what your values are going to be. So there's alpha. We need mu. I think I should have been more descriptive with that mu. Let's call that on paper, well, on digital paper, mu naught, to really emphasize this is the value that came from the hypothesized value in the null hypothesis. And that's what we called it right over here as well, mu zero. So alpha, mu zero. Last is just sigma over root n. This is inherited from the central limit theorem. So sig over square root n. And that takes care of the first line. Then on this line, we're just inputting z into a new function, p norm z. You have to be mindful that we're using a different value for mu, using mu a. Then what else is left? Last part is directly the same, sigma square root n. So with all this set up, well, let's call it power, just to emphasize that's what we produced right here. But then I want to output power as well, so I'll just rewrite it down below. And hit Control A, Control Enter. It tells us the power of the test is 1. I was not expecting that. It should not be 1 in a sample size 10. I was expecting like 30%. Something is a little bit off with what I input here on one of these values. Huh. Anyone happen to see what it was? Let me double check my syntax as well. It's always exciting when your syntax does not go the way you thought it was going to go. Let me scroll up above just to double check my values up here. So we have 5% significance level, so that one was right. We have sigma at 0.5. No, I think that's what it was right here. It looks like the sigma was right at a 0.5 on this one. So if we break that down to a 0.5, run this again. Let's see what we get out. Control A, Control Enter. Yeah, that's what I was expecting on that run right there. One small mistake causes some weird aberrant behavior down below, but we've got it, folks. The power of the test at a sample size of just 10 is just shy of 60%. And that means the probability of a type 1 error would be 1 minus power, about 40% for probability of type 1, probability of type 2 error. Type 1 error is still just alpha. Well, we've got it, folks. We now know what the power of the test is, but it still doesn't answer the direct question of what sample size is required so that we get 95% power. So that's the next thing that we're trying to fine tune and adjust. Well, let's go back to the syntax. Now that we have it, let's maybe double the sample size. Hit Control A, Control Enter. We're at 85% power. There are smarter ways to do this. You can get really wild and do a power graph that tells you the power at integer n is 1, 2, 3, 4, and so on. It just shows how power increases as a function over the integers. But we're not trying to get too involved in this computation. Think of this as just playing around with it, introducing what the power of the test is. And so we're doing this in kind of a silly way, just plug and chug. So I'm going to double the sample size again. That's great, but we wouldn't get full credit for this answer. The trouble is, sure, power is at 98% and it sounds fantastic, but the people designing the study want it cheap enough so the power is just at 95%. So we went too big on this. Let's drop it back down. Maybe we went from 20 to 40. Let's do 30. Power of the test is 0.9496. This is where the judgment calls come in. But it's similar to what we were doing when we were designing a study involving a confidence interval. Recall up here, way up here. This is doing the same sort of thing. What sample size do we need for a margin of error of 5 milligrams per deciliter? When we got here, we said round up, because we want the most conservative estimate of the sample size so that we really hit that margin of error once all is said and done and we collect data. Same on this problem. If we got to, say, 94.96%, not good enough for us. We want to get just above 95%. This is the point where you want to increase the sample size really just by 1 and see what the effect is on the next run. At sample size 31, it's exceeded the power that we wanted, but that's the smallest sample size that gets us there. So this is what we would inform people. If you're running this test and all information here is accurate, particularly the sigma value is shady, but if everything is accurate, we would inform them use a sample size of 31 to target your required level of power. Well, I'll put this all down below. To obtain power equals 95%, set n to a sample size of 31. So that's the whole outcome of this syntax right here. Let's share it right away. And it looks like we're pretty much done with that power computation. I have some side concept type questions that we want to take a look at after having done this. But any questions or comments so far, folks, to this stage? Okay, one question I would have after coming up with sample size 31, targeting power equals 95%, let me fix that a little bit. This is really power equals 95.50%. We should be honest that we overshot this a little bit, but that's just based off the math of the problem. We couldn't do anything about it. 95.05%. Set the sample size to 31. But what does this all really mean? Let's do a little follow-up on this. I'm going to box it to convey the problem is over right here, but we just have additional remarks. One remark I would have about this is, what does power equals 95.05% even mean? Let's address that right away. Power equals, I'll just keep it as a percentage, 95.05% means to really address this, we need to take another look at our hypotheses one more time. So let me scroll up and grab them. Oh, geez, actually, this might be the better screenshot. It has everything, the significance level, the null, the alternative, and the specific alternative. That's critical in interpreting power. So for our interpretation of what power really means, we can say if n equals 31, the sample size we produced, then there is a 95.05% chance of correctly concluding down here, we're concluding that the alternative hypothesis is what we're supporting, that we have significant statistical evidence in favor of it. So we're correctly concluding the mean rainfall in the forest. It's a Canadian forest, but we're being a little bit terse in writing this out. The mean rainfall in the forest is, I should be targeting this with the red dot. That's our actual alternative. Less than a pH of 5. And this isn't quite it. To really say what you've computed when you came up with that value for power, 95.05%, the last part is, given that the real mean rainfall is actually exactly 4.7 coming from the specific alternative. So that's what power has achieved for us. When the experts, whoever they were, meteorological, ecological people, told us that the effect size was 0.3, what they were trying to get at us was a high probability of rejecting the null hypothesis when the alternative is true, but only slightly true at 4.7, the smallest distance where if it was a 4.8, we wouldn't have even cared about it. So we found this smallest effect that's important and got a high probability of actually detecting that effect once we run the hypothesis test. This is what a real statistical study designing would really look like at the very beginning. All these huge considerations of what a type 1 error is, a type 2 error is, how to find 2 alpha, and then making sure you really run the study with the right sample size so that you have a high probability of finding the smallest effect of which is of importance. Maybe the effect is bigger and then the power is just way higher, but we want high power at the smallest possible effect of importance. It's a lot of words to say it all, but does the logic of this make sense at the moment? Okay, so that's remark 1. Remark 2 is we harped on and on about probability of type 2 error. We still haven't computed it, so let's compute it as well. So we know the power at sample size 31 is 95.05, and remark 2 is probability of type 2 error equals, it still uses the same specific alternative that got us the power computation, but now we just go 1 minus 0.9505, giving us a value of, let's find out, 1 minus 0.9505. We have a value of 0.0495. It's pretty close to alpha, but that's only a coincidence. What you get for beta in general has nothing to do with what you set alpha to. It had everything to do with what the sample size was, rather. Well, any questions at all, folks, on getting through either one of those remarks? Okay, I find that this type of logic right here, again, It's a lot. There's lots going on. I mean, there's two curves we're considering. There are three hypotheses you're considering: the null, the alternative, the specific alternative, which is informed through the effect size. There's just a ton to synthesize here. So when you're doing this homework, if you get lost at any point, please don't hesitate to email. This is one of those sections where it's kind of like RStudio. There's no secrets. We're all just getting exposed to it for the first time as an introductory topic. And if it seems vague and foggy, please don't hesitate to reach out. I agree with you. It takes a lot to really internalize all this information. And what we're going to do next is concept questions relative to the power of a test. So that's what's coming up next. Part E asks us the question, if alpha decreases, that's the significance level alpha, will the power of the test increase or decrease? Now, when you're chewing on that, let me grab some graphics. There's really two ways to answer this kind of question. One way is visually, just look at the diagram that we created. Imagine whatever we're looking into changing. Actually, let me grab a larger screenshot here. I want to go from the specification of the model itself as well. So one way to think about this is imagine something changing in this picture, which is hard because this is a humongously dynamic picture. As alpha moves, a lot of stuff moves. Or the second approach, if you're more of the analytical thinker, just change alpha right here and see what happens to power. And both ways are great ways to answer this sort of question. Let's start just visualizing this. It says alpha decreases. What would that mean? If alpha decreases, this area in purple gets smaller. And if that happens, Z has to move to the left so it actually captures the right amount of area to the left of it under the green curve. If that's the case, power goes up to this black bar, and that black bar is moving to the left. So it looks like if alpha decreases, the power of the test also decreases. They go in the same direction, in other words. But that might not have been super convincing to you because, again, it's an involved diagram, and if one thing changes, several things are changing all at once. So let's see if this is really true. My claim is the change in alpha matches the change in power as well. Decrease means power decrease. Let's run the syntax again. Power's at 95%. Go to alpha and decrease it, 0.01. This would make industry happy. We've greatly reduced the probability of a type 1 error. Let's check our power though. It's dropped down. So that's in the same direction that we were expecting. Reduce alpha, reduce the power. In effect, if you reduced alpha, Z moves to the left and the power region in purple just starts to shrink more and more and more. So we can say here, if alpha decreases, power does as well. And just for the sake of kind of memorizing this type of content, let's put down a little extra statement. Alpha, power, change in the same direction. What I mean by same direction is increase alpha, you've increased power, decrease alpha, you've decreased power. So their directions of change go in the same direction. Well, that's one thing you can absolutely influence at the start of writing out a hypothesis test. You can determine before collecting any data at all what your alpha will be, so we could fine tune that. The next question is, what about effect size? That you cannot fine tune. This is informed by experts. It's not something we just guess at. When someone informs us in a certain context, the effect size should be this or that, 0.3 in this problem, or was it, hang on. Yeah, 0.3 in this problem. We're just constrained to working with that. Changing the effect size after the fact would be massively unethical. You're not doing the spirit of the statistical problem any longer at that stage. But what happens if you do decrease the effect size? That's a tricky one. Any volunteers to say what should happen? Let me think about that. Yeah, I agree with you. Let's see what is influenced by the effect size. The effect size gets rolled into that alternative hypothesis, right? Our effect size in this problem was 0.3, and it was a left-held test. We literally took the 5 here, subtracted 0.3 to get that specific alternative. That means, let me think about this again. Hang on. So if the effect size was 0.3 here, but we say that it decreases maybe to a 0.1, this would become a 4.9, right? So the smaller the effect size, the closer your specific alternative is to the value in the null hypothesis. But if it's a 4.9, the center here gets closer to 5 now. And if that's the case, well, this vertical black bar doesn't move, but everything else does. So I think I'm kind of getting lost in the logic. This might have been what you said. I think if the effect size decreases, so does the power. But oh, gotcha. Yeah. Oh, gotcha. Yeah. Awesome. Let's see if that's really true, because again, this is a lot of like mental backflips, right? One thing changes, affects another thing, affects a specific alternative, moves one of the curves in the distribution, but not the black bar. That's a lot to visualize. So the analytical way would say, let's come back over here, fix alpha first, double check our power, make sure it's reset. And we said effect size decreases. Decreasing the effect size gets this closer, let's say 4.9. And power has dropped enormously when we decrease the effect size. It's now barely at 30%. Let's see if we can capture the essence of all this in one statement. If effect size equals 0.3, HA mu would be equal to 4.7. And this is the specific alternative. I'll just say alt for alternative. If effect size equals 0.1, say, specific alternative HA becomes mu equals 4.9. And now we can say a decrease in effect size. I think I need more space here. Let's just drop this down. A decrease in effect size causes a decrease in power. We saw it two ways, kind of imagining what's changing dynamically in the diagram, but also just cranking it out and seeing the drop in power, the precipitous drop in power. And going in the other way, let's suppose we increase the effect size. Here it is at the default, effect size 0.3 in pH. Let's say the effect size was 1 unit of pH. This would drop to 4. And now the power isn't 1, but it's so high that because of the finite nature of the system, it just rounded it to 1. Let's say the sample size was 4. At sample size of 4, power is gigantic. So this is huge in terms of effect size. It has a lot of influence on what the power is going to be. So let's go back to 4.7, 31, reset this syntax back to our normal level of power. But last comment on this one is that effect size and power change in the same direction, just as the significance level of power. And so far that's pretty convenient in a way, right? It means you don't necessarily have to think too hard about these things if this pattern continues forever, except it doesn't. There's always got to be something that breaks the pattern, it seems like, in statistics. And that's this one. It says here, if the sample size decreases, will the power of the test increase or will it decrease? Well, Let's first think about this without considering any diagram whatsoever. That's a bad outcome, right? Lowering your sample size is getting us less accuracy on everything. So if the sample size increases, power of the test, I said there's one that doesn't go in the same direction. I might take that back. I would expect it to decrease as well. Would you all agree with that just assertion there? It's not really based on anything other than a principle of that's a bad outcome since dropping the sample size. We shouldn't be rewarded with higher power. That seems totally nonsensical. Let's see if we can justify it first visually. If the sample size decreases, what happens really? There's no change on 4.7. The center is the same here. There's no change on 5. The center is the same there. So what would you all say happens to this diagram? Any volunteers? Yeah, go ahead.
Would it shift to the right, not right, left?
Not necessarily. The centers themselves would stay exactly the same, but something does shift. So depending on how you mean by shifting, something does happen and it shifts in the left and the right on both of them all at once. Because think about this part right here. If the sample size decreases, the change is right here. A decrease in the sample size means this is getting bigger. If this gets bigger, it's talking about the variability of the distribution itself, how spread out it is. And if it's more spread out, your pictures start to look like this. But centered at 4.7. The one that's in green starts to look like this. But centered at 5, this is kind of tricky. And now that means this is really just too much to see at once, but imagine everything has been widening out. What then happens is that black bar changes a lot, and it's going to cut into power a tremendous amount at smaller and smaller sample sizes. What we want is large sample sizes and makes these narrow. And when they're super narrow, they start to look like this. Essentially, it's hard to take this and really capture that all at once. But that's what narrowing happens when we decrease the sample size. Less variability, the peaks get higher, and the tails start to close in. So it looks like the power should decrease. Feels like it, but let's put it all to the test. Run it one more time just to make sure we're getting the right power level. We targeted this at sample size 31. Now, sample size 3. That's an immediate outcome, right? Smaller the sample size, smaller the power. This is one where it seems intuitive just reading it. It's directly easy to see by running the syntax, but it's actually extremely hard, at least for me, to visualize just on the diagram. These are kind of tough questions in a way, but I was wrong when I said power doesn't go in the same direction on all of these. It does on this one. That was my mistake there. We'll say here, smaller sample size. Directly gives smaller power. So once again, even on this problem, sample size and power change in the same direction. And sample size is absolutely something we can influence as well in the study. That's really what we were doing when we were trying to compute power. We're just increasing the sample size until power itself increased to the right level. Well, that's the end of the concept questions. Really, it's just an opportunity to think about power a little bit more and see how it could be influenced by making some design choices, changing the sample size, some unethical design choices that we should never make, never change the effect size, unless the experts inform us that we just have updated information, which should cause it to be changed. We never do this willy-nilly. Or if we change the significance level alpha, But we should only make that change if it's well informed by managing type 1, type 2 error, not because we're trying to increase power. Well, that's pretty much the end of this section. The last parts are just a couple of follow-up statements on what would you do if the tests went this way, right tail test. Any questions at the moment, folks, before we finish off these last statements? Okay, let's drop this in. So let me go to the syntax we just produced. And this is basically it, except if it's a right tail test, that means right over here, let's go actually look at a graphic to help inform us why we're doing this. But in a right tail test, we take the alpha and drop it on this end right here. Z would go on this end as well with it. And we would be using Q norm with area to the right. So if that's the case, we'd go down here on Z and put in lower dot tail equals false. And let me make a really big change up here before we share this. This is now for a right tail test. That'd be terrible to forget. Then once we get that, this is now harder to visualize, but the power curve relative to the blue distribution is also to the right in a right tail test, which means the black line also to the right. We're getting the area in purple to the right of the black line now. But area to the right here just means lower dot tail is false. So that's what it would look like. It's going to look crazy in this syntax right here because these values are not right for that kind of computation. But keep in mind, you would change all these first, and then the information would work out right. So let's take this and share it as well. Oh dear. There we go. So that's how the syntax would work. Definitely want to share that because the homework exercise is a right tail test. And now let's add maybe just one last thing. It occurred to me that we were mentioning a lot last time we were looking into hypothesis testing and talking about it the first time, that the two-tail test is the default test. It just so happens it's also the harder test to calculate power on, because if we do a two-tail test, we take alpha, this one, we cut it in half and we split it into one tail and the other tail. And even though this curve gets close to the x-axis, there is still some area here. So now we need two p-norm computations in the two-tail test. Let's share that syntax as well, just for the sake of just total completeness. I included it in the chapter 15 folder on Moodle, but not on my thumb drive. Let's go to Moodle then. Over here just earlier today. So this is for the two-tail test. Let's drop that in. So if you're doing a two-tail test, this is the computation you would use. I didn't ask a homework question on that. This is, again, more for the sake of completeness. But I have Z left, Z right, because now alpha is split into two. Here's alpha over 2 on these things. And we now have to find critical numbers in 2 spots, probabilities in 2 spots. It's kind of a mess in a certain sense. But you know what we're really going to do is we are treating chapter 14 and 15 as just a way to get started thinking about inference. We're later going over to chapter 17. There it is. And in chapter 17, RStudio itself has a lot of built-in functions for just computing the hypothesis test, just like that. T.test is the function. T.test is overloaded to also give a confidence interval. And you just use different syntax, call a different function, just to find the power of that test. Feed it the hypotheses, the effect size. And RStudio is doing all this kind of stuff under the hood. We're looking at it from scratch, just so that we know what power is, what it looks like, before you just go in RStudio, click a button, and it's like you're feeding information to a black box. This is telling you what's really happening, even if it's in a different distribution, different hypothesis test. But at this point, looks like we've completed chapter 15 in its entirety. It's kind of breaking. Let me make sure that saves. There we go. Next chapter we'll get into is chapter 17. But any last questions or comments at the moment, folks? Okay, I don't have a lot of time to really get into chapter 17, but I do want to leave you with one kind of graphic that goes along with it. Let's open this up. Go to Desmos. We're making a big correction in this chapter. In chapter 17, we're finally admitting, no, we do not know the population standard deviation sigma. Our whole goal is to estimate the population mean, the parameter mu. We have to admit we probably know nothing about the population sigma as well. It's only in very rare situations where we have great legitimate information on sigma. So if we knew sigma, we'd be dealing with normal distribution 0, 1. And this is the distribution for p-values. This is the distribution for critical numbers and confidence intervals. I just want to make a quick adjustment here. Go -1, +1. That would do the job. But now, once we admit to ourselves we don't know sigma, we do this next thing. We go and say sigma, usually color code that green, is approximately equal to S. Then our test statistic that was Z, X bar minus mu naught, sigma over S, becomes a T test statistic, X bar minus mu naught over S now, the sample standard deviation. That's the data we actually have knowledge on. Divide by the square root of n. But there are some issues here. When we finally admit resoundingly that sigma is an unknown, we've lost a lot of information about the statistical problem. When we put in an estimate, we have, well, to include that uncertainty, that this was just an approximation. And like we've said all along, we don't even know how good it is until we quantify the margin of error in making that approximation, just like with mu and X bar. But someone really very clever, William Seeley Gossett, also known as Student T's distribution publisher, came up with this distribution. It's the T distribution, and it's depending on the degrees of freedom, n -1. Let's add a slider here and say n starts at 2, goes up to 100, and it's an integer. This is the T distribution. And notice the big effect on this. Oh, I didn't want to do that. On the T distribution, well, let's first recall the red curve is the normal distribution. Blue curve is the T distribution. And if we were to go from, say, -1.95 or 96 to 1.96, geez, that's hard to hit. There we go. Relative to the normal curve, that's central probability about 95%. That's us doing a 95% confidence interval, and your critical number is about here. However, if you want to do a 95% confidence interval with respect to the T distribution, it's going to be a lot tougher. Let's say, how about -3, +3? That's only 80%. Well, not even quite. How about -4, +4? Still not there. -6, +6? It's close. But look how many units you have to extend to the left, additionally, over the normal distribution and to the right. It's a lot. So things are looking pretty bleak so far, except here's the other really interesting fact about these distributions. The T distribution shape is dependent entirely on the sample size. And that makes sense. It's capturing the uncertainty in this estimate, but the uncertainty in that estimate evaporates the larger your sample size n gets. So if n increases to, say, 3 or 4, watch what happens to these curves. The T distribution converges in probability as a real limit to the normal distribution. And right around samples of 30-ish, I still can't really tell the difference between the two. Around samples of 4 or 5, there's a big difference. And that's where William Seeley Gossett became famous for his work. He worked at the Guinness Brewing Company, and his sample sizes were this low, doing experiments on yeast, trying to come up with the best beer, a worthy pursuit, I suppose. He noticed the statistical methods, Ron Fisher was involved with this, are not working out when we just plug S there. He came up with the T distribution, corrected the logical loophole, looped in Fisher, who was thought of as the preeminent statistician at the time of what's going on, and they both worked together to make this distribution famous. The reason I call this gentleman a role model for people in the sciences is that the Guinness Brewing Company did not want this to happen. This gave them the edge on making the perfect beer over everyone else. So they informed William Sidley Gossett, you cannot publish this work. You are paid by us to come up with this distribution. It's ours. It's proprietary now. William Sidley Gossett invented a pseudonym, the student, invented a distribution, student's T distribution, and he just released it regardless. But because he did that work, statistical methods had a humongous head start. If this was kept secret the whole time, it would have eventually been discovered, but how many years? 10, 20, 30? That's a big open question. And this is something that's happening all the time. There are mathematical theorems, algorithms, statistical methods that are considered proprietary information even now. You can almost guarantee it. People like, say, Google, the NSA, and so on, have lots of interesting methods that are proprietary. But if anyone ever just released them, it sounds like corporate espionage, it could really be to the benefit of all mankind in that case. So in my view, this is a great role model for people in the sciences, probably the best example I have. And we'll take a really close look at his work when we come back on Tuesday's class next week. I keep forgetting which day we start on. But this is the idea of what we're getting into. Fix that problem, we don't know sigma, change the distribution, but everything else stays exactly the same. We'll interpret our confidence intervals the same way, our hypothesis tests the same way, we'll frame them the same way. It's just a new distribution we're getting into. But we'll save all that when we come back to class next time. Any questions at the moment, folks, so far? Okay, well, have a great night, folks, a great weekend. Any questions do come up while you're working these homework problems, I'll be available to help out. Don't hesitate to reach out. See you all later.
Thank you.
Yep, take care.
Have a good weekend.
You as well. Thanks, you too.